All right. So since no one is here, it's okay. I'll do this lesson at my own pace and I'll post it on YouTube for you guys to consult later. Op amps are a very important concept for you guys to know, particularly in Division C silo. You definitely need to know these very well, but they're a lot easier than they seem. So let's get to it. The op amp is this three-terminal device, okay? Symbolize it with this triangle symbol. And it's dictated by this equation right here. The output voltage equals whatever gain the op amp has. This parameter is the gain parameter times the difference of the voltage between its two terminals. So V plus is the non-inverting input because there's no negative in front of it, whereas V minus is the inverting input because there is a negative in front of it. And in practice, we assume AOL is infinity for the ideal op amp. Okay. But for real world devices, it's still very large. It's about 10 to the fifth, 10 to the seventh, or even more than that. Okay. So, uh, hello. Yeah. So
Hi.
I just got started on the lesson. I'm just recording it and then it will be on YouTube, what I
Okay.
said. But basically, this is all I've said so far. Um, the ideal op amp is a three terminal device. Okay. And it has an inverting and non-inverting input. And it's governed by this equation at the top right, where for ideal op amps, we assume that gain parameter, AOL, is infinity. A open loop is what we call it. In reality, the op amp has these power rails. It has a positive limit and a negative limit that prevent the gain from boosting V out beyond those rails. So like say that this is 3 volts and this is negative 3 volts, then the difference between them is 6 volts. But if my positive limit is plus 5 volts and my negative limit is minus 5 volts, my output can't be more than 10 volts. It's just not possible.
Okay.
So for actual real world circuits, that's what it looks like. So if your input voltage looks like this, your output voltage might look like this, right? It might just jump between the max and the min values. But for ideal op amps, we assume the gain is infinity. And so when we analyze op amp circuits, there's really two rules that we, or three rules, but first we'll talk about these two that we need to keep in mind. First of all, no current flows into or out of the op amp terminals. Okay, the current can flow out of the output, but current can't flow into or out of the input terminals. And yeah, so current can't flow into or out of the input terminals. And when we analyze circuits with op amps, in practice, what it comes down to is writing the Kirchhoff current law expressions with the input terminals and assuming that no current goes into there. That's a very important thing to remember. And even for real world op amps, this is the case because in practice that those terminals are the gates of some MOSFETs. And so current can't flow into there. And if any current does, it's a very small amount. The other assumption, golden rule that we make is that the open loop gain is infinite. Okay. It's an assumption and simplification, but even for real world op amps, it's very, very large. So let's talk about the most simplest op amp circuit that we can easily analyze. So in this circuit, we've made V plus equal to 0 volts. We've made V minus connected to both the input and the output voltages. Okay. And our goal is to solve for a relationship that connects V out to V in. We want an equation there. So first of all, let's just write where the currents are going. So no current goes into here. That's not a thing. That doesn't happen. The current only goes here and only goes there from this node. Okay. Now that means we can write the voltage at this node as V minus. And so the current through this resistor is just V minus minus V in. That's the voltage drop divided by R1. And then the other current is V minus minus V out over R2. And since those are going in the same direction, we add them together. And there's no current going in, so it's just equal to 0. This is the same thing we've been doing with nodal analysis for a long time now. So it should be comfortable with this. Um, Now, V out is going to be equal to the open loop gain times V plus minus V minus. However, V minus is set to 0 volts because of the ground. Okay, so this right here is 0 volts. That's what, sorry, that should say V plus set to 0 volts. So that's that. V plus is set to 0 volt because of ground. Okay. So if V plus is not equal to V minus, the output voltage is going to be massive. Remember that V out, ooh, that was terrible. V out equals AOL times V plus minus V minus. Okay. So if there's any difference between V plus and V minus and AOL is infinity, then V out is also going to be infinity. But that's not possible. V out can't be infinity. So in a case where the output can do something to the input, the output is actually going to drive these to be equal, and it's going to force this term to be zero. Because if there's no difference, then V out can indeed then V out will become infinity. But remember that this term then becomes something like infinity times zero, and this is not infinity or a zero. If you do any calculus, what this looks like in practice is a an indeterminate form. And so it could just be like a number. And so we don't actually know what infinity times zero is. It's just some mystery thing. Okay. And so V out is not necessarily zero if this term is zero. However, if this term is not zero and this term is guaranteed to be infinity, then V out will be infinity, and that's not possible. So that's a bunch of words to say that V plus and V minus are driven to be the same voltage. In other words, we drive that voltage difference to be zero. Okay. Hi, Ethan and Evan. So I already got started a bit, but the video will be posted on YouTube, so you can watch the first bit to see what you missed. Um, so yeah. So V minus has to be 0 volts, and V plus is already 0 volts because we've tied V plus to ground. And so if we substitute those into our equation here, then we get this. And then if we do some algebra, we can rearrange and write that V out equals negative R2 over R1 times V in. So now we have an equation that relates V out to V in terms of our resistors. And we can see that V out is basically some fraction times V in, some inverted fraction. So if I make a plot over time, say my V in looks like this, okay? That's my V in. Then what my V out will look like is basically this. Depending on the value of R2 and R1, is going to be some amplified or some de-amplified version that's also inverted. For that reason, we call this the inverting amplifier. It's basically the most common application of an op amp. It takes some input voltage and magnifies it based on the values of R2 and R1. And we can tune that magnification by tuning the values of R2 and R1. And remember, to derive this equation, all we did was use nodal analysis. We didn't do anything special. It was just pure nodal analysis. And so we realized another key golden rule for the op amp, okay? The first two golden rules that we discussed were that no current goes into the input terminals or out of the input terminals for the op amp, and that the open loop gain is infinite. And we use those two assumptions to derive this equation for the op amp. And in doing so, we found that whenever we have a situation in which there is open loop, or in which the output is connected to the input, the output will drive the two inputs to be equal, because we don't want to have an infinite output voltage. We want to force the difference between the inputs to be zero so that we don't have an infinite output voltage. That's only true in configurations with feedback. So if my V out is not connected to either of my inputs, I'm not going to have that rule be true. So it's only true in a feedback loop configuration. We call it negative feedback. But in this case, they are connected, and so we have that rule as true. Now, the actual architecture of an op amp is pretty complicated. We talk about it in basically three stages: the differential input stage, the gain stage, and the output stage. The differential input stage basically takes the voltages between V plus and V minus and figures out the difference between them. The gain stage takes that and amplifies it hugely using what's basically a CS amplifier circuit. We're not going to talk about that, but that's what it's called. and then the output stage electrically isolates that from the rest of the circuit. Now, this is too complicated for us to go through, obviously. Even in a class that covers op amps in detail, you won't cover this because there's just not much point. But it's important to remember that under the hood, an op amp is still just based on transistors. So I think I have actually, let's see, do I have it with me quickly? Yes, this chip right here is the LM324. I don't know if you can see that, but what it is basically the most ubiquitous op amp chip. And so in the same way that we had logic gates on chips, we also have op amps on chips. But, yeah. Now, oops. Okay, I don't want to talk about this, but this is just a buffer, okay? V in is forced to be equal to V out here. Okay? That's all this is. V in has to equal V out because they're tied to the exact same node. Okay? And again, you might be confused because you say, oh, well, V out equals the open loop gain times V plus minus V minus. But remember, AOL is infinity. Okay? And if this term is zero, we get an expression that's like infinity times zero. That's not infinity, but it's also not zero. It's just like some number. It's called an indeterminate form. If you've done calculus, you know that this term is not zero or infinite. It's indeterminate. We don't know what it is. And so even though V plus is zero, so V in has to be zero, or rather V in is the same thing as V minus, that doesn't mean that V out is also going to be zero. So V out just is exactly what V in is, but this is a buffer. And so what this does is it electrically isolates V out from V in. We can do whatever we want to V out and we won't mess with it because we're using this op amp to force these two voltages to be equal. A more concrete example of an interesting op amp circuit is this configuration. So it's not really obvious what it does at first. So let's go through and analyze it with nodal analysis again. So we have feedback here. So V plus is equal to 0 volts. So V minus is also equal to 0 volts, okay? And let's just use nodal analysis to solve it from there. So we have a current in that direction and a current in this direction. And actually, we're going to split that current into three more currents. One current here, one current here, and one current here, okay? That should be pretty obvious that we can do that, right? This current's going into those three resistors, and so those are the three places that it goes, okay? The current going up is going to be 0 minus V out over R1. The voltage before is 0. The voltage after is V out. So 0 minus V out divided by R1 gives us that current, okay? For these resistors, instead of writing this one current right here, we're going to just write the sum of these three currents. So the voltage here is 0 volts, and the voltage after is V in. So all their voltage drops are 0 minus V in. But each of them have a resistance of R2, R3, and R4. And you can combine them using the parallel rule for resistance, and you'll get the exact same result. It's just more explicit to do with nodal analysis here. So now if we take that equation, do some algebra, we can rearrange it to look like this. Negative R1 V in times the sum of the reciprocals of R2, R3, and R4 gives us V out, okay? And so what this does is it sums the voltages right here, and right here. So now imagine I separated them right here and I had different voltages connected to each of these. V in 2, and then I had V in 3 connected here. Then I can actually sum the voltages depending on the value of these resistances. Okay, and you should use nodal analysis and try to solve for that yourself. That's called the summing amplifier, where we can sum different voltages together to get a V out at the ratio of R1 over whatever resistance is here. Okay, and that's a really useful circuit in any application where, for example, say we had a circuit like actually, I don't have it on this computer, but say we had a circuit that just like in block diagram form, split some input signal into a low frequency part, a middle frequency part, and a high frequency part, okay? But then we wanted to recombine those, okay? Then we just use a summing amplifier between them, okay? We just put a summing amp. and get our output. So if, like on the volume controls in your car, you can adjust, not your car, you're too young, but on the volume controls in a car, you can adjust the bass, the treble, and the mid. That's basically what it's doing. It splits the voltage into low, medium, and high with pass filters, which you didn't talk about, but those are another type of circuit that basically filter out different frequencies. And then they recombine those voltages with the summing amplifier. So, yeah. So it's a short lecture, but here's a summary of what we've talked about. You can now analyze op-amp circuits that do all sorts of interesting things. For example, this circuit right here is the integrator circuit. If you remember the capacitor was dictated by our differential equation that I equals C times dV dt, where V is the voltage across the capacitor. Well, since I have a differential equation there that dictates the current, when I do my nodal analysis and solve for it, what I get is that V out is actually the integral of V in over time. And if I put the capacitor here instead, I'd get that V out equals something, and then the derivative of V in over time. So I can make differentiator and integrator circuits as well. I can make all sorts of interesting things with these op amps and interesting configurations. Um, but there's three things to remember when you do analysis, particularly if you guys are here for ScioVirtual purposes. You can solve any op amp. Most ScioVirtual test writers don't actually know op amps very well, and so what they do is they just look up an equation for a standard configuration. You can just write down all the equations for all those configurations and be fine. You'll get by. But op amps are really easy to solve just in like a minute. But if you know the key rules to analyze op amp circuits with, and so you can outsmart your test writers and like just do better than them. And there's the only two things you need to remember are no current flows into or out of the terminals of an op amp, okay? There's no current going in and there's no current going out here. There's no current going in and there's no current going out. This does not happen, okay? So any current that goes in here goes up here, okay? No current goes into or out of the terminals. The other thing is that ideally the op amp's open loop gain is infinite. Remember that the output voltage of an op amp, the voltage right here, V out equals V, or sorry, A open loop, that gain parameter, times V plus minus V minus. Okay? Ideally, this parameter right here is infinite. Okay? And as a result of that, the voltage of V plus and V minus has to be the same if there's any connection of V out to our inputs. Okay? The reason that is because if this is not zero, if this term right here is not zero, then this term right here is going to be infinity. But we don't want infinite voltage. If it is zero, we get that infinity times zero in the equation, and that's an indeterminate form, and so then V out can just be a number. But if it's not zero, then we just get infinity, and that's no good. So if there's any form of feedback, if there's any connection of V out to our input voltages, then the voltage of the two input terminals will be driven to be the same. So in this case, since this terminal is 0 volts, this terminal will also be forced to be 0 volts. Okay? And yeah, that's it for op amps. So it's a short extra lesson, but really there's not much to talk about. They're not that difficult to understand. So, are there any questions for the three of you guys? Because if there aren't, I'll just end it, and that's that. Really, the summing amp is the main circuit that you'll see in ScioVirtual. That's the one that they think is just complicated enough to write you, but it doesn't involve any calculus. But really, the capacitor based ones for the differentiator and the integrator are useful. And actually, op amps are commonly used for active filters. So you can very strongly attenuate certain frequencies of voltage signals in the AC regime. But again, AC analysis is not of interest for us. So yeah. Anything? All right. I'll just end it there. There's
Bye.
no question. See you guys. Thanks for showing up.